Have you ever stopped to think about what holds something the size of a skyscraper in place, but in the middle of a raging ocean? You might picture a giant anchor, right? But the real hero of the story is something we see all the time and probably take for granted: the chain. Now, I know, it looks simple, but what we're about to explore is honestly one of the most incredible feats of industrial engineering on the entire planet. It's a process of fire, immense force, and unbelievable precision that creates a literal lifeline of steel. Okay, let's dive right in. So take a look at this thing. This is not just a ship. It's what they call a floating production, storage, and offloading vessel, or FPSO for short. A much easier way to think of it is as a completely self-contained industrial island. You've got a power plant, a refinery, a chemical processing facility, and a massive storage tank, all floating in water that can be miles deep. These are multi-billion-dollar assets. They're home to hundreds of crew members, and they're tethered to an irreplaceable energy source thousands of feet below. The craziest part? They are engineered to stay right there on that spot for 20, maybe even 30 years without ever going back to a port. They just operate non-stop through anything and everything the planet can possibly throw at them. Which leads to the big question, right? What is the tether? What holds this colossal structure steady against the just relentless grinding force of 100-foot waves and winds that are strong enough to rip buildings apart? What is the one thing, the only thing, preventing an absolutely catastrophic environmental and economic disaster? Well, the answer is a whole web of massive mooring chains. Each individual link can weigh as much as a car, and these chains anchor the whole floating city to the seabed. But how on earth do you even begin to forge a chain strong enough for a job like that? To get that, you really have to imagine a factory floor that's just unlike any other. It's a place where the air itself just hums with immense power. You've got these giant custom-built machines performing what looks like a carefully choreographed ballet of extreme heat and truly unimaginable pressure. I mean, this isn't just bending metal. This is a symphony of steel and force, literally transforming raw metal into an object of almost mythical strength. Every single step you're looking at here is its own little marvel of physics. It all starts with a solid bar of a special steel alloy. And when I say special, it's like a chef's secret recipe of iron, carbon, and other elements like nickel and molybdenum, all designed for just extreme, extreme toughness. Those bars are cut to an exact length. Precision is key, to make sure every link has the perfect amount of mass. Then comes the heat. And this isn't some open flame. It's an induction coil, this huge copper ring that creates a powerful magnetic field, and it heats the bar from the inside out to over 1,600 degrees Fahrenheit. It is glowing like a piece of the sun. A hydraulic press then bends this glowing hot bar into a perfect U-shape and hooks it right through the last link they just finished. And here is the real magic, the flash weld. Copper jaws clamp onto the two ends, and they blast it with a colossal electric current. We're talking hundreds of thousands of amps, like a controlled lightning strike. The steel at the ends instantly liquefies. In that exact split second, a press slams them together with so much force that they are forged into a single, seamless piece of metal, right down to the atomic level. It's just incredible. Finally, as you see in that last step, the extra molten stuff, they call it flash, is sheared away, and that central support bar, the stud, is pressed in and welded, locking the whole link into its final immensely strong form. And this is really the crucial point here. This isn't just about bending hot metal. This is high-precision metallurgy. Every single variable, the chemistry of the alloy, the heating time, the exact temperature, the amperage of that weld, the pressure of the forge, it's all meticulously controlled. The whole goal is to make sure that the molecular grain structure of the steel in the weld is as strong or, maybe even stronger than the original uncut bar was. It's kind of like baking a world-class cake. If you're 1 degree off or 1 second too long in the oven, the entire thing is compromised. But as it turns out, not all of these giant links are made in exactly the same way. And that brings us to the two main characters in our story. You've got the stud link and the studless link. Now, at first glance, they might look pretty similar, but that one small difference in design has enormous implications for how they behave under pressure and, of course, where they get used out in the wild. And this just illustrates the difference perfectly. So on the left, you can see that simple open oval shape of the studless link. And on the right, there's the stud link with that very distinctive bar in the middle. That's the stud. It really seems like such a minor addition, doesn't it? But in the world of extreme engineering, that single piece of metal changes absolutely everything about how the chain performs. This table really breaks it all down. So that stud, it basically acts like a structural support beam inside the link. See, when you put it under immense tension, a normal oval link wants to stretch out and get narrow.
But the stud pushes back against that. It maintains the link's shape, and that makes it stronger for its size. And maybe even more important, it prevents the chain from kinking up and getting knotted. I mean, can you imagine trying to untangle 100 tons of knotted steel on the deck of a ship in a storm? The stud just makes the chain behave itself, keeps it orderly. And that's why it's perfect for things like mobile drilling rigs that are constantly lifting and resetting their anchors. Now, the studless chain, on the other hand, is lighter and cheaper, which makes it ideal for permanent moorings, like on our FPSO. It gets laid on the seabed one time, and it's left there for decades. That 9% weight difference might not sound like a lot, but believe me, when a single chain can be miles long and weigh thousands of tons, it adds up to a massive saving in steel, in fuel to transport it, and in the size of the ship you need to deploy it.
Okay, so you forged your chain, link by perfect link. You followed every single step with scientific precision. But how do you know? How do you know for sure that it's strong enough? Well, now comes probably the most dramatic part of the whole process, the moment of truth. This is where the product of all that fire and force gets subjected to a trial by truly unimaginable tension. So manufacturers use two completely different tests to guarantee the strength. First up is proof testing. Now, this is non-destructive. The entire chain, every single link, is locked into a colossal stretching machine, and it's pulled to a load that is far greater than its designated working limit will ever be. It's like testing a new bridge by driving a convoy of trucks across it that's twice as heavy as it will ever need to support in real life. If it holds up without any permanent stretching or damage, every single link is certified. Then, you have break testing, and this is the complete opposite. A small 3-link sample is sacrificed. It's put into a machine and it's pulled with more and more force until it violently snaps. The goal here isn't to certify the chain, it's to validate the engineering, to prove that the steel and the whole manufacturing process can actually withstand the forces that the designers predicted it would.
And the forces we are talking about here are just staggering. This number, over 2,400 tons, that's the pulling force a top-grade chain sample has to withstand before it breaks. To put that into perspective for you, that's the weight of about 400 bull elephants all pulling at once. It's the combined thrust of 3 space shuttle main engines at takeoff. And all of that mind-bending force is concentrated on a single piece of steel, pulling it apart until its atomic bonds finally give way in this catastrophic, explosive release of energy. Right, so here's the bottom line. There is absolutely zero room for error. This is not statistical quality control, where you test 1 in 1,000. No. Every single link that goes into the ocean has been individually proof tested. And then, samples representing that batch have been physically destroyed to guarantee the ultimate strength of the design. Only when this absolutely brutal, exhaustive process is complete is the chain finally deemed ready for service. But here's the thing. Forging the chain is only half the battle. The moment it's deployed, it begins a decades-long war against an environment that literally never rests. Its strength was born in fire and force, sure, but now it's going to be tested by slow, silent, and often totally invisible enemies. The chain is fighting a war on multiple fronts at once. You've got corrosion, right? Salt water is literally eating away at the steel. But then there's also metal fatigue. The chain is constantly being stretched and relaxed by the waves, kind of like bending a paperclip back and forth millions and millions of times, slowly weakening the steel's internal structure. There's something called out-of-plane bending, which is where twisting currents wrench the links sideways, stressing the welds in ways they were never meant to handle. And then there's fretting. At the exact point where 2 links rub together, the immense pressure and the tiny little movements create microscopic wear, a grinding that can create tiny surface cracks. And those tiny cracks, those are the starting point for a catastrophic failure. And this is exactly why those tiny hidden cracks are so terrifying. So an FPSO might have, say, 12 mooring lines. There's a redundancy built in. If one chain snaps, the platform should be safe. But now, the 11 remaining chains have to share the load of that broken one. And if they've all been exposed to the exact same conditions and they've been weakened by the same invisible flaws, that extra stress can cause a second failure, and then a third. It's a cascade failure. And as this research paper confirms, this is not just a theory. There have been actual cases where these floating cities have broken completely free. That is a multi-billion-dollar disaster scenario. So, how do you fight an enemy you can't even see on a piece of equipment that's operating in total darkness, under crushing pressure, thousands of feet below the surface? Well, you deploy a new kind of weapon. Cutting-edge robotics armed with advanced physics on a mission to hunt for the tiniest of flaws before they ever have a chance to grow. The key technology here is called non-destructive testing, or NDT. And honestly, the analogy on the slide is perfect. Just like a doctor uses an ultrasound to see inside a patient without doing surgery, engineers use NDT to see inside a link of solid steel. Their goal is to find those hidden cracks, especially in the most critical and hardest to see area, that contact point where two links are constantly rubbing together. And this is the inspector. This is not a human diver. That would be impossibly dangerous down there. No, this is a remotely operated robot, built specifically to withstand the deep ocean. It literally clamps onto the mooring chain and just methodically climbs its way down, link by link by link, carrying this sophisticated sensor package with it, all while streaming data back to the engineers sitting safely on the surface. The robot's superpower is a really specialized form of ultrasound. It presses a sensor, a transducer, against the steel and sends a guided wave of sound at a very specific frequency, rippling through the link. Then, the system listens for the echoes. You can think of it like shouting at a canyon, right? A clean echo comes back. You know the canyon wall is solid. If you get a strange, jumbled echo back, it tells you there are caves or ledges over there. It's the same idea. A perfect link returns a clean, predictable echo. But if there's a crack, even a tiny one hidden from view, it disrupts that sound wave and creates an anomaly in the echo. The software can then pinpoint the exact location and size of that flaw, which lets the engineer schedule a replacement long before it ever becomes a failure. So in the end, yeah, we come all the way back to that old saying, a chain is only as strong as its weakest link. But what we've really seen here is that the true strength of these colossal lifelines doesn't just come from the brute force of their forging. It comes from the intelligence and the relentless vigilance used to find a weakness that is completely invisible, hidden deep within the steel and deep beneath the waves. It's really a testament to human ingenuity that to control the immense power of the ocean, we have to rely on both a symphony of incredible force and the faint echo of a tiny, perfect sound wave.